Hello student, good morning. I am Dr.A.K, Professor of Chemistry. Now I am going to start Gibbs energy change and equilibrium. Last class I have discussed Gibbs energy. Last class I have discussed Gibbs energy. Now I am going to discuss Gibbs energy change and equilibrium, how both are related. Okay, Gibbs energy change and equilibrium. Okay, how both are related, that I am going to discuss. Now this we have seen how a knowledge of the sign, means positive and negative sign. We have seen how a knowledge of sign and magnitude of the free energy change of a chemical reactions allows. What are that? First, predicts, we can tell by the knowledge of Gibbs energy change, we can predict of the spontaneity of the chemical reaction. First. Second, prediction of useful work that could be extracted from it. Here always you keep in mind free energy, that is the delta G, that is equal to delta H minus T into delta S. Or you can understand free energy is actually energy difference between H and Ts, because S is dependent on temperature. That's why T always will be with S. Then G is equal to H minus Ts, just in general way. Otherwise, exactly delta G is equal to delta H minus T into delta S. Then difference between this delta H minus T into delta S, that is the free energy. Then in a general way you can understand like this also, free energy, Gibbs free energy change, that you can understand like that also. Suppose you have 1000 rupees in your pocket and something you have purchased of 300 rupees. Then now 700 rupees with you, 300 already you have invested. Then that 700 now you can use for the other work. Okay. Then here this 300 is just like entropy change, T into delta S. Why? Because for the entropy change, means disturbance, energy is used. Okay. In that it is spent. In that work it is spent. That is T into delta S. That is called unavailable energy. Okay. Because that is spent in just in disturbance. Disorder. Molecules become disorder. Then in that disordering energy is required. That's why it is invested there. Then that is useless work, unavailable energy. That amount which is utilized here, that is not available. That is called T into delta as unavailable. One question I have given last class, in last video, based on that only. Then this always you think from the total now some energy used, that is now that energy is not available. The money you have spent 300 rupees, that is not with you now, and only 700 rupees with you. Then 700 is the, you can say, available energy. 700 rupees, just like 700 rupees, whatever means remaining is there, that is the available energy. then always you think like that. Difference between both delta H minus T into delta H, whatever difference is there, that is the available energy for work to do useful work. Okay, this concept you keep in mind, then free energy you will understand very clearly. In solving the numericals, this concept will be useful. And always think, keep in mind, delta G should be negative for a spontaneous change. Delta G must be negative, less than 0, okay, for a spontaneous change. Again, just like one more general example for a spontaneous I am giving you. Suppose any leader comes, very popular leader like you can say Vajpayee, then all people will come simply without invitation. They will come to listen him. No invitation. Simply they will come to listen him. They like them. They came. A large number of people will come to listen him. Okay. He has not invited anybody. Simply they came. Then that is spontaneous. But sometimes you might have also seen in real life, some leader, when they will come, nobody will go. Then possibly they will give money and something gift they will give. Then possibly they will bring. Then that is the non-spontaneous. Okay. This way also you can understand the meaning of spontaneous and non-spontaneous. Okay. Then falling water from hill to down, that is a spontaneous. All you can say irreversible reactions are spontaneous. Already I told you, all natural reaction, irreversible reaction are spontaneous. Okay. Then now just I briefly given you concept of Gibbs free energy. Okay. Then how Gibbs energy is related to equilibrium, both has relation, that I am going to discuss. So far we have considered free energy change in irreversible reaction. Now we are going to discuss, now we will examine the free energy change in reversible reaction. Reversible, already I told you, whenever the word reversible will come, think like a reverse, means reactant to product, again it will come back, product will convert to reactant, then reactant to product, and again it will come back, product to reactant, and this will continue. That is called reversible situation. Then reactant to product, one arrow you write, half arrow, and another half product to reactant, double arrow, but half arrow, one arrow towards product, other half arrow towards reactant. Then this is a sign of reversibility. Then reversible meaning you should clearly understand. Already I told you, I think you will understand now. Reversible under a strict thermodynamics sense is a special way of carrying out a process such that system is at all times in perfect equilibrium with its surroundings. Means system and surroundings both are in equilibrium. When applied to a chemical reaction, then what will happen? When applied to a chemical reaction, the term reversible indicates that a given reaction can proceed in either direction simultaneously. Okay, simultaneously from either direction, means from reactant side also, from product side also, so that a dynamic equilibrium is set up. Because always there will be movement. Dynamics means motion. Reactant to product, motion. product to reactant, again they are in motion. That's why it will look like a static. There are two equilibrium. One is called a static equilibrium, other is called dynamic equilibrium. Then here we are talking about dynamic equilibrium, reactant to product, product to reactant. Then when this system, when reversible is applied to a chemical reaction, the term reversible indicates that a given reaction can proceed in either direction simultaneously, so that a dynamic equilibrium is set up. This means that reaction in both the direction should proceed with a decrease in free energy. This means like that both side free energy should decrease. Only then a spontaneous reaction will take place. But here this is impossible, which seems impossible. Okay, then what is possible? It is possible only, means both side reaction should take place. It is possible only at equilibrium. Okay, it is possible only if at equilibrium the free energy of the system is minimum. Free energy change, because if too much difference is there, reactant or product in energy, then this reaction will not take place. Reversibility will not take place, because there is difference of energy, reaction and product. Too much energy change is there. That's why condition is that energy change should be minimum. Then you can say then a product to reactant is possible. Okay. Then this things means reversibility is possible only if at equilibrium the free energy of the system is minimum. If it is not, the system would spontaneously change to configuration of lower free energy. Okay, it is not fully. Okay, it will not come in the full equilibrium. Okay. Then what is, suppose I am telling one example. Suppose A plus B is in equilibrium with C plus D. In equilibrium, reversible reaction A plus B, sign of reversibility C plus D, means A plus B is giving two product C plus D. Then here delta G, change in free energy, must be zero, Z-E-R-O, keep in mind. Delta G for this reaction A plus B is converting to C plus D, and both are reversible, and for the equilibrium delta G not only minimum, there should be zero. Then dynamic equilibrium, they will be in dynamic equilibrium, means from reactant side it will go to product, from product it will come to the reactant, when difference in both reactant and product free energy should be zero, delta G should be zero. Only then you can say equilibrium will take place, and equilibrium will be called dynamic equilibrium. Don't forget this condition. Question is also asked that at delta G, at equilibrium, what will be the value of delta G? Then delta G should be zero, and delta S entropy also should be zero. At equilibrium, delta S, change in entropy, also remains zero. This also remains zero. I am telling you, don't confuse. 1 marks or 2 marks question they are asking. Now we come to the Gibbs energy. Then Gibbs energy for a reaction in which all reactants and products are in a standard state. Standard state, I told you, it's how it is indicated. Then here it is indicated by, you can say, just zero script, a small zero script it is mentioned, means if you will put this 0 script above G, then it is called a standard G. If you will write 0 at the top of S, then a standard entropy, standard G, standard H. Just 0 means above 0, inside a small, you can say, line you can put, a 2 or a 2 point you can write. That's enough. That is called a standard. And meaning of a standard means a standard temperature and a standard pressure. Already I have discussed. Okay. Then here you should understand that this standard G, then a standard G has a relation with ordinary G. Ordinary G means G at any temperature. Delta G at any temperature, maybe 10 degree. What is the value of free energy at 10 degree or 15 degree or 20 degree or 50 degree, 60 degree, at any temperature? That is called delta G. But if you will use a standard delta G, it means you are talking about standard condition of temperature and pressure. Then a standard temperature, already I told you, 273 Kelvin. 273 Kelvin means 273 plus 0 degree. 273 plus 0 degree, then 273 Kelvin. Absolute zero is different. Absolute zero is different. That is a minus 273 K. Okay, that is called zero, absolute zero temperature. Absolute zero. Okay. Then here I am pressure, standard pressure, that is 1 bar. Then when temperature is 273 Kelvin and pressure is 1 bar, then that is called a standard condition of temperature and pressure. Then now delta G and standard delta G both are related. How both are related? That is most important. Okay. And delta G and standard delta G both are related by, now I am telling you, that is the delta G is equal to a standard D plus RT ln K. Here R meaning is the same, universal constant, and R value gas constant, universal gas constant. RT is the absolute temperature. ln means natural logarithm, that you can convert into the log by multiplying 2.303. Okay. Then here, and K is the equilibrium constant. K is called equilibrium constant. Then G is equal to, ordinary G is equal to delta G plus RT ln K. This relation is most important relation in solving the numericals based on thermodynamics. Okay. Then delta G is equal to a standard G. Delta G is equal to a standard G plus RT ln K. Where K is the equilibrium constant. And actually now this class, what I am telling you now, this will be the last class of thermodynamics. Next class I will start equilibrium. Okay. Then you will know more and more. From the beginning I will discuss equilibrium. Then here K is the equilibrium constant, and general meaning of K I am telling you. Suppose A plus B is converting into C plus D. In the middle sign of equilibrium you have written. Then K is equal to product divided by reactant. K is equal to product or products, you can tell. Product or products divided by reactant or reactants. Suppose A plus B is converting into C plus D, then concentration of C into concentration of D divided by concentration of A into concentration of B. That is called K. K is always constant. Then this is because this situation is at equilibrium. Means when reactant is going to product is coming to the reactant, reversible condition. And that's why it is called equilibrium constant. Okay, I will tell details and when I will start equilibrium chapter. Okay, then K, I told you meaning of K. Then concentration term is used by showing it in keeping in a big bracket. Then in big bracket, C, simply C you can't write. C you write inside the big bracket. Okay, in big bracket, both sides you keep. In big bracket, C you have written. After that, multiplication side. Again, you in big bracket, D you have written. C into D. Down, in bracket you have written big bracket A. Again into B in big bracket. Big bracket means concentration. It shows concentration. Then in equilibrium actually concentration is also expressed in terms of partial pressure or pressure. Pressure you can tell. In terms of pressure also concentration term is represented, because if suppose reactions are going, gaseous reactions are going on, gaseous reaction, then gas, how can you tell in the term of concentration? Then that concentration term indirect way you can tell in the terms of pressure or partial pressure. Only here I have told you. Okay, because many numericals they will ask based on pressure, they will not give concentration value, they will give pressure value. Okay, now then here I was telling you that delta G is equal to standard delta G plus RT ln K. This is the most important relation. Then here at equilibrium condition, delta G value will be 0. Delta G value will be 0. Then 0 is equal to standard delta G plus RT ln K. If you have pen and paper, you note down this relation also. Okay, always when you are attending the class, keep pen and paper. Okay. Then here I told you at equilibrium delta G is equal to 0. Then 0 is equal to standard delta G plus RT ln K. Then what will be standard delta G value? Then standard delta G value will be after transferring left side. Then you will get standard delta G, that is equal to minus RT ln K. Minus RT ln K. Already I have sent this relation also in the last video or before that also. Then this is very important relation. It came from the first relation also. This relation, when you put delta G is equal to 0, then this relation came. Okay, and many relations are many numericals are solved in all examination. Thermodynamics numericals based on thermodynamics, it is asked in almost all examination. Okay, IIT, medical, UPSC, sometimes when means here CSIR net exam, they will ask more. Okay, in scientific examination selection for any scientific post, these questions are asked. Then now actually here this delta G value, I have told you how it is related to K. How delta G value is standard delta G is related to K, I have told you. And one thing already you are knowing. When you are knowing that delta G, standard delta G is related to K, then again you can correlate. You know that delta G is equal to H minus Ts. Already you know. delta G is equal to also is equal to delta H is equal to delta H minus T into delta S. Already you are knowing. It means delta H minus T into delta S, that is equal to minus RTLN K. Okay, see how all three are related. It means you can tell standard delta G is related to, or standard delta G is equal to delta H, standard delta H minus T into standard S, and that is equal to minus RTLN K. All three are related. This is also most important. Okay, for entropy, okay, these things I am telling you, it has relation with entropy, free energy, and K. I have told you this K has related with enthalpy also. All four relation. This relation if you will keep in mind, then you can solve many numericals without any problem. Because G is related to H and S, and again G is related to K. Hence any numericals based on H, S, K and G you can solve. Hence always you keep in mind delta G, standard delta G is equal to standard R, standard H minus T into standard S, and that is equal to minus RTLN K. For a strongly endothermic, now condition you understand. For a strongly endothermic reactions, the value of delta H, the value of standard delta H may be large and positive. Endothermic means always delta H will be positive. Okay, then and in endothermic reaction H is supplied. You are knowing. Then delta H will be positive, and heat may be supplied more also. Then for a strongly endothermic reaction, the value of delta H may be large and positive. In such a case, value of K will be much smaller than 1. See, relation when you will see, or also in general you keep in mind, when endothermic reaction, in the case of endothermic reaction, and even you are applying more heat, then rate of reaction will be very, very less. Okay, that K value will be very, very equilibrium constant value will be very, very less than 1. This condition you remember, because question is asked, and reasoning you can understand by seeing the relation minus RTLN K. Then here T is a positive temperature. If it is supplying, then obviously temperature will rise, and minus RTLN K, then T is what? T is more, then minus value will come. Then actually that K value will be very, very less than 1. Okay. Another case you can see in these things. In the case of exothermic, what will happen? Endothermic, you understand that K will be much smaller than 1, and the reaction is unlikely to form much product. It will not make much product or more product. In case of exothermic reaction, delta H is large. You know that heat will come out. It will liberate energy and value will be negative. For the exothermic reaction, delta H will be negative and it will release too much energy also. Then in that case, delta G is likely to be large and negative 2. Value delta G value will be more, because now actually this negative delta H value is negative and enthalpy is more. Enthalpy is more. Okay. And in this situation, delta G is likely to be large and negative. In such cases, K will be much larger than 1. This question is asked. Remember this also. Both are reverse. Endothermic, if you remember, exothermic reverse way. More product it will give, because K value is more. If the value of K is more, it means production is more. Keep in mind. Okay, K will be much larger than 1. We may expect strongly exothermic reaction to have a large K, and hence can go to near completion. Reaction will be fully complicated, complete reaction. Reaction will be completed in this case. Delta G also depends upon delta S. Already I have discussed. Delta G also have relation with delta S. If the change in the entropy of reaction is also taken into account. Okay, if delta S and delta G both are related, 4 relation I told you. Delta G, delta S, delta H, delta G, delta H, delta S, all are related. Okay, then this delta G also depends upon delta S. If the change in the entropy of reaction is also taken into account, the value of K or extent of chemical reaction will also be affected. If delta S of the reaction you are taking into account, then K depends upon S also. Okay, the value of K or extent of chemical reaction will also be affected depending upon whether delta S is positive or negative. Okay, then this I have told you about these things. Gibbs energy change and equilibrium. This concept is very, very important, and there are some relation. Okay, condition, you can tell condition, that because I told you delta H, delta S, delta G all are going to be affected by temperature. Then effect of temperature on a spontaneous reaction or on a spontaneity of the reaction. You should understand then how this temperature affects delta H, delta S, delta G, and finally how it will affect to the spontaneity of the reaction. Then that relation I may send you in the this video also. And by concept is very, very important. As for example, you can say if delta G is negative, just I am telling you here, I understand, I will try to send it also. If delta H is negative and delta S is positive, then delta G will be negative. And when delta G is negative, the reaction will be spontaneous. For the reaction, you can say, for a reaction to be spontaneous, delta G must be negative. That you keep in mind. Then here, delta H is, if delta is negative and delta H is positive, then delta G will be negative and reaction will be spontaneous. Like that way, if delta H and delta S both are negative, delta H also negative, and delta S also negative. Both are negative. Then delta G, when temperature will be less, then delta G will be negative, and when delta G is negative, the reaction will be spontaneous at low temperature. Okay, now like that way two three cases are there. Whether you will by seeing, I will try to send it, then you will understand better. But only here I want to tell you, if plus will come, then non-spontaneous. Finally, whatever will be the H or S value, okay, finally if delta G is coming negative, then spontaneous, and if it is coming finally positive, delta G is positive, then non-spontaneous, whatever be the temperature. Okay, temperature whatever be, that finally delta G should be negative, then only reaction will be spontaneous. If it is positive, coming positive, then this thing will be non-spontaneous. And always you should understand the low temperature in thermodynamics, low temperature and high temperatures are relative. Sometimes low temperature difference maybe you can say 0 degree or 5 degree. Okay, 0 degree and 5 degree. And that is also 5 degree difference, and 60 degree and 65 degree. That is also temperature difference of 5 degree. But see, there is a difference in heat content. Heat content difference is there. Hence always it is relative. Okay, now I am going to just some numericals I will discuss. Okay, that is important. Now we should understand, because theory portion is finished. All thermodynamics full theory portion is finished. Then now this relation on delta G, few numericals are there, 2-3 are there, I will discuss. Okay, that your concept will be more clear. Question I am reading, you can automatically you will understand it, because I have already explained it. Question is like that. Problem I am telling you. Problem, 3 problems are there, I will tell you. Then here, first problem, numericals, that is called numericals also. Calculate standard delta G. Calculate standard delta G for conversion of oxygen to ozone. Oxygen is O2 and O3 is ozone. Then oxygen is converting into ozone at 298 Kelvin. If Kp for the conversion is 2.47 into 10 to the power minus 20. Okay, this they have given Kp value is 10 to the power minus 29. 10 to the power minus 29 is there. Okay, then you have to calculate the delta G value. Reaction they have given, balanced equation is 3Y2O2 and product is O3. Okay, 3Y2O2 is reactant and product is O3. Temperature is 298 Kelvin. Kp value is 2.47 into 10 to the power 2.47 into 10 to the power minus 29. Minus 29. That is the Kp value. Kp value. I will tell you what is the Kp value. That is Kp means that is the pressure at equilibrium. That is called Kp. Pressure at equilibrium condition. What is the temperature? What is the pressure? Then pressure at equilibrium. To maintain the equilibrium, pressure is required. Then Kp value is given here. Okay. Then now I can solve it very easily. formula already I told you that standard delta G is equal to minus 2.303 RT log Kp. You have converted ln into log, then Kp. Then now we can see how it is easy to solve the numericals. You have to calculate delta G, standard delta G. Then standard delta G is equal to minus 2.303 RT log Kp. This already I have told you relation. Then here all things are given. R value you are knowing 8.314 joule per Kelvin. Correct? Log Kp, K value already given. Kp value is given. Okay. Actually, log K is there. That time when you are solving, you have to calculate Kp. Then you write Kp only in the place of K. You write Kp, not only K. Kp. Then Kp value is given. Then all value is given. Then no problem in getting the result. Then after putting all this value, then you will get delta G value. You will get, because here one thing you keep in mind, that R value is in R value is 8.314 joule per Kelvin. Joule per Kelvin per mole, not kilojoule. Joule only. Hence result you will get after putting all values, result you will get in joule. That is, you will get 163,000 joule per mole. Joule. Then now you can convert in kilojoule. A small k you can write. Then you will get final result 163 joule, kilojoule per mole. Okay, that's the final result. Now second problem you can see. Second numericals. Find out the value of equilibrium constant for the following reaction at 298 Kelvin. Reaction is given. 2NH3 plus CO2, these are the reactant. Product is ureas, means NH2CO, NH2, aqueous. Okay, urea is in aqueous solid, in a liquid way, plus H2O. This they have given. Cancer reaction 2NH3 gaseous form plus CO2 gaseous form, sign of equilibrium. Product is NH2CO, NH2, that is in liquid state, aqueous, plus H2O. This is a relation given. Also they have given a standard free energy change at the given temperature is minus 13.6 kilojoule per mole. Standard delta G value is given minus 13.6 kilojoule per mole. Then you have to calculate Kp value. You have to calculate here equilibrium constant, not Kp, K value you have to consider equilibrium constant. Then again this is very easy. Thermodynamics, all you can say, numericals are easy actually. Only thing you have to understand, and relation you have understand. Many expression I have told you, derived also. Then that relation you have to keep in mind. And thermodynamics, you can say, problems are easily you can solve. Then here nothing is there in this question. That already I told the relation that this minus delta G is equal to what? Minus 2.303 RTLN log RTL log minus 2.303 RT log K. This is a relation. Now all things are given. Then log K value now you have to find out. You put all value. Standard delta G value is given. Only in the beginning the standard G this thing, standard delta G value is given. Then standard delta G is given. Then after that, what is remaining? R value is also given. R value is also given. You already know. And T is also given, 298 Kelvin. Then delta G value are knowing, T value are knowing, R value knowing. Then you know that minus delta G is equal to 2.303 RT K. RT log K. Hence log K is equal to minus delta G is minus standard delta G divided by 2.303 RT. Okay, log K is equal to minus standard delta G divided by 2.303 RT. Then here now you put the value, and after putting the value you will get the value of log K. Log K value will get. That will come after putting the value, its value will come 2.38. Its value will come 2.38. Now you should know actually log table. You must know to see the log table or anti-log. Anti-log table you must know. For full chemistry concern numericals, to solve it is required. Many times it is required log table, particularly in chemical kinetics, thermodynamics, and in equilibrium chapter is required, and many places is required in gaseous state sometimes also. Hence you must know how to see the log table or anti-log. Okay, and now log K value you are knowing. Log K is equal to 2.38. Then what will be the value of K? Then K value will be, just by use of anti-log table, you will come to know its value is 2.4 into 10 to the power 2. 2.4 into 10 to the power 2. Okay. Then this I have solved two numericals. Third one, that is a little long, not means 3 concept is required here. Now problem I am telling you, there are 3 concept is required, and is it fit for the advanced IIT examination. Then here now just you understand. Question I will read it. At 60 degree centigrade, dinitrogen tetraoxide N2O4. Dinitrogen tetraoxide is 50% dissociated. Calculate the standard free change of this temperature and at 1 atmospheric pressure. Again I am reading one more time. At 60 degrees centigrade, dinitrogen tetraoxide is 50% dissociated. Calculate the standard free energy change at this temperature and at 1 atmosphere, means atmospheric pressure. Then here first you see delta G they are asking to calculate. Calculate the standard delta G, free energy. Then what is its formula? Then first you see the formula what is required. Then delta G, standard delta G is equal to minus RT ln Kp. Because it is a gaseous reaction, dissociation reaction, N2O4 is converting to NO2. You have to write. in your answer. First reaction you have to write. N2O4 is converting into 2NO2. Balanced equation you have to write. N2O4 sign of equilibrium 2NO2. Both are in gas. That's why here K will be Kp. K you can denote as a Kp. Then this Kp value you have to find out, and then you have to use this formula. Delta G, standard delta G is equal to minus RT ln Kp. Then here RT not a problem. Kp you don't know. Delta G you want to calculate standard delta G. Then Kp how will you calculate? That is a new things. Actually that is related to Chem equilibrium chapter, but I will give a hint here. Then as soon as you will know the value of Kp, then quickly you can calculate the delta G. Then how will you calculate Kp? That I am telling you. That's why I am telling you 2-3 concept is required. Then here first you have to write the, you can say, reaction. Okay, first you have to write the balanced equation. And temperature actually already given. Then now according to the question, it is N2O4 is 50% dissociated. 50% dissociated, not fully. Suppose 1 mole N2O4 was there, then only half mole dissociated. Half mole is remaining, half mole only dissociated. And if you will see the balanced equation, 1 mole of N2O4 is giving 2 mole of NO2, 2 NO2. It is giving 2 NO2. Means 1 mole is giving 1 mole N2O4 is giving 2 mole NO2. 2 mole NO2. It means 0.5 mole will give 1 mole, double. 0.5 mole they will give 1 mole NO2. Correct? This is important thing, very important things I told you. Then now reactant side, how much remained? Then reactant side, it was 1 mole, half mole dissociated. Then only half mole is remaining. And product side, it is 1 mole is remaining. Understood? Product became 1, and the reactant side only half is remaining. And product side double means half became double because 2 NO2. Then now this I told you. Then mole fraction you have to calculate. Mole fraction of N2O4 and mole fraction of NO2. Then already I told you in gaseous state that mole fraction is equal to, here you can write mole fraction of number of moles of N2O4 divided by total number of moles of N2O4 and NO2. Same way for mole fraction of NO2, you will write number of moles of NO2 divided by total, means a number of moles of N2O4 plus number of moles of NO2. Then in case of N2O4, it will be how much? Only 1 minus half, only half is remaining. Reactant means N2O4. Then 0.5 divided by total. Total means what? Reactant is half and product is 1. Reactant is half mole was remaining, and product is 1. Then 0.5 plus 1 means 1.5. Okay, 0.5 plus 1, 1.5. Then 0.5 divided by 1.5. 0.5 divided by 1.5. That is the mole fraction of N2O4. Same way, that side for N2O2, that is there 1 mole was there. 1 mole means 2 into 0.5. 2 into, because it is 2 NO2 is there, but got 0.5, half mole. Okay, then 50% only converted. Then 2 NO2, then half became double. Half became double because of 2 NO2, double. Then here 1 divided by total the same. Total is the same what was in the case of N2O4. Means 1 plus 0.5. Product side 1 mole and reactant side half mole was remaining at equilibrium situation. At equilibrium 1.5 mole was there at equilibrium situation. Okay, for reactant also total same, for the product also same. Then mole fraction of NO2 is equal to how much? 1 divided by 1.5. 1 divided by 1.5. How 1.5? I told you. Okay, product side 1, reactant side 1.5. Then now mole fraction of both you are knowing. For N2O4 and for NO2 already you have calculated. Then mole fraction when you are knowing, then also I told you, I have already taught you how to calculate partial pressure. Okay, then in partial pressure mole fraction is required. You remember, to calculate partial pressure mole fraction of the gas is required. Then nothing you have to do, just you have to multiply by the given pressure. Then given pressure is here, they have given 1 atmospheric pressure. 1 atmospheric pressure is given, means into 1, you multiply by 1 in both partial pressure of N2O4, just mole fraction into 1, and same way here for NO2, mole fraction into 1. Then now you got partial pressure, means mole fraction is the only partial pressure in this situation, because given pressure is only 1. Hence what was the, you multiplied by pressure is 1. Hence now you got the partial pressure of both gases, N2O4 and NO2. Okay, then now partial pressure you got. Third concept here, I told you three concepts are there. Then now you calculate. First you have written reaction, balance reaction. You have calculated, you can say mole fraction or mole fraction or partial pressure finally calculated. Then partial pressure is treated as concentration. Already told you, partial pressure is treated as concentration. And now again a new concept that already I told in the beginning, K is equal to product or products divided by concentration, reactant. Product divided by reactant, that is the K value. Already that is the concentration multiplication of products divided by multiplication of reactants, that is the C into D divided by A into B. But here you have to keep in mind what is the coefficient. Suppose A plus B is equal to C plus D, then suppose A is 2, B is again 2, means 2A plus 2B, you are getting, suppose 2C plus 3D you are getting. Then coefficient will, this is called coefficient. Then this coefficient, when you will write the K, that time coefficient will go as a power of concentration. As for example, C into D divided by A into V you have written. Then C, suppose power was, coefficient was 2, then C square, C power 2. D power was 3, coefficient was 3, then it will go D power 3 divided by A. A is suppose 2, suppose it was 2, then A power 2. Okay, and B was also 2, then B will be also power 2. You have to write like that. Okay, then this is the way to write K, equilibrium constant. Then now this concept you are going to use here. then you will come to know the value of Kp. Actually in equilibrium chapter we will discuss more. Many Kp value will get, Kc and Kp value. Okay. Then here Kc means C means concentration, Kc and Kp. Then here now Kp value you got. And now Kp value you got, then just you have to substitute the value in the formula. Delta G is equal to minus RT ln Kp. Now Kp value is known. Then Kp value you will get 1.33 atmospheric pressure. That value you will get. Okay, after putting all the things, reactant products and reactants value, whatever I told you, that Kp is equal to here to calculate the Kp value, that is the partial pressure of NO2 square. Means NO2 is 2 NO2 is there, and NO2 power 2 it will go, divided by N2O4. Means partial pressure of NO2 power 2 divided by partial pressure of NO2. Means down only no power, only one power of NO2. Power of NO2, pressure of NO2 power 2 divided by pressure of NO2. After putting the value, it is a square, keep in mind, a square. Then partial pressure of NO2 you have calculated, that value you keep here, a square value is there, power 2, and down only no square, only one partial pressure of NO2. Okay, partial pressure of N2O4, partial pressure of N2O4, that also value you have to keep, that is no power is only one, because only one was there, because it is giving N2O4. N2O4 is giving 2 NO2, that's why NO2 became power 2 and N2O4 is only 1. Then you put the value, then you will get value, Kp value will get 1.33 atm, atmospheric pressure, and this value you keep in the formula, that is delta standard delta G is equal to minus RT ln Kp. Then now all value is known, then you will get relation. Then after putting this value, then you will get final result, delta G, standard delta G is equal to minus 763.8 kilojoule per mole you will get. After putting the value and solving it, you will get result, you will get in minus 763.8 kilojoule per mole. It means delta G is negative, means it is a spontaneous reaction. Reaction is spontaneous. Okay, delta G is negative. Understood? Then this I have told you some numericals, and then again I will send some solved numericals, maybe 1, 2 unsolved also, you should try. Okay, now I am stopping only here. Again I will meet in the next class with next new chapter, equilibrium. Thank you.